Okay, today we're going to learn about making images with lenses. Just got back from my conference and realized I have this proposal I need to do, but there's not a video for you, so I'm going to do this first. Thank you for giving me a good excuse to procrastinate working on this proposal. Do something fun instead. Here we go. So, when we look at images through lenses, we're making images in a very similar way to the way that we make them with mirrors, only instead of reflection bending the light, we're bending the light with refraction. So let's take a simple case. A lens has two surfaces. Let's consider just one surface to make life simpler for now, and let's make that surface flat. So imagine we're looking at a fish. Here's our fish down here, down in the lake, and where does the fish appear to be? This surface is going to make an image of the fish. When I look into here, it's not going to look like the fish is down here, it's going to look like the fish is somewhere else. So how do I figure out where the image of this fish will form? Well, let's look at some point on the fish, and let's send rays away from that and see how they bend. Alright, now, a ray coming from the fish that's going straight up, normal to the surface, doesn't bend when it goes to the surface. But a ray that's going, my fish is down here. I'm imaging a point right here, alright? So if my fish were right here, a ray of light coming from the fish in this direction, when it hits the surface, it's going to refract according to Snell's law, right? And I'm going from something of a high index to a low index, so we're going to bend away from the normal, alright? So it looks like, if I put my eye up here, it looks like these rays are actually coming from a point down here. So it looks like the fish is actually right there. It will actually appear to be closer to the surface. The image will be closer to the surface than the actual fish, than the object. Alright, well if I label that theta 1 and theta 2, I remember Snell's law, and then I'll go and put some labels on here. Of course, this distance right here is the object distance p. This distance right here from the surface to our image is, of course, not q, but negative q, because, right, my eye's over here, the image is on the opposite side of the surface from my eye. It's on the side where the light doesn't go, and so I get a virtual image here, and q is negative. Negative q goes with virtual image. Alright, and then I've got two triangles that share a common side, and I've got some angles, and you can do a bunch of trigonometry and algebra, make some small angle approximations. What do I mean by small angle approximations? I'm making these angles small. In other words, the paraxial rays approximation, that I'm only considering rays that are close to the optical axis. When I do those approximations, I end up with this. I'm not going to go through all the details, but there you go. We can figure out how far from the surface the fish appears to be. Right? So we get an image distance that depends on our object distance, and then the index of refraction of the two medium. Now what if I had a curved surface? Imagine I have some object and I'm finding some image forming here, or some object in here trying to find the image over there. I can do a similar sort of thing, drawing normals and rays and angles, taking the paraxial ray approximation and so forth. Alright? So with a curved surface you can do this as well. We're not going to go through all of the details and all the derivations. I just want you to know that a lens is just two curved surfaces, and the light bends as it goes through each surface. Alright? But in this class we're not going to go into a lot of detail about how the light curves at each point. Alright? We're going to characterize each lens by a focal length. If I have a lens, I can just tell you how does this lens make images? Well, it's got a focal length f. If it's a converging lens, it has a positive focal length. So a converging lens, imagine a lens that looks something like this, alright? And if I send rays of light into it, those rays will all, collimated rays, so light from a flashlight infinitely far away, alright? Those rays will all come and cross at some point right here, and that distance then is the focal length, alright? So I take an object at infinity, its image will form one focal length away, and that's how I find the focal length of the lens. Or I could calculate, alright? But that's how I could measure it in the lab. Alright, and then a diverging lens, so for example, imagine I have a lens that looks like this. If I have rays of light that come in, for a diverging lens, they all bend away as if they were coming from some point over here, right? So if I take an object at infinity, my diverging lens will make a virtual image of it. Alright, and the distance is right here. So from my lens to that focal point, this is negative f, because f is negative for a diverging lens. Okay, Equations. The equations we use to find the image location when I use a lens is exactly the same one I use for a mirror. 1 over f is equal to 1 over p plus 1 over q. Alright, so if I have a focal length for my lens, then I can use this equation. The difference between a mirror and a lens is, first of all, light goes through a lens instead of reflecting like it does on a mirror. So positive q will mean that the light went to that the focus is on the opposite side of the lens from the object, whereas with a mirror, positive q, they're on the same side. Q is always positive when the image forms on the side where your eye is looking at it, all right? So that's one difference between mirrors and lenses. The other difference is this focal length here. For a mirror, the focal length is just 1 over the radius, or radius of curvature over 2, or for a diverging, it's negative the radius of curvature over 2. But that's only for a mirror. For a lens, it's different. It's different physics, right? A mirror is the law of reflection. For a lens, we're going to use refraction. And I'll show you the equation we use to find the focal length of a lens. It's a little more complicated, all right? So those are basically the differences. But it's the same equation. Once you know the focal length, it's very similar physics, although it's refraction instead of reflection. Now, how do you find the size of the image? All right, it's the same that we get with a mirror. The magnification is still minus q over p. Of course, q means it's on the other side. So with a mirror, we were able to show kind of like if I have a converging mirror and I have some object right here, we said, look, boom, I have this ray of light over here. And by symmetry, if I have an image form over here, the size of the image, I've got similar triangles, right? If I look at that reflection right there. And so it makes sense that it's minus q over p. Imagine instead that I have a converging lens. What happens if I've got an object right here, the light, instead of reflecting about the normal, it goes straight through, and right, because at the very center of my lens, that's where the optical axis is, the surface is perpendicular to the optical axis, so on both sides of the lens, if it bends here, it unbends on the other side by the same amount. So when we draw our rays with a lens, we'll have one that doesn't reflect about the middle, it just goes straight through the middle, and once again, we have our similar triangles, and we find that the magnification is minus q over p. So these two equations are valid whether we're dealing with lenses or mirrors. All right, here is the equation we use to calculate the focal length of a lens. I'm not going to go through the derivation here. If you really want to be a master of physics, you can go through and use Snell's law to find this. All right, this equation, first of all, it assumes, so imagine you have two spherical surfaces, all right, and these surfaces have a radius of curvature 1 and a radius of curvature 2. All right, from those radii of curvature, you can calculate this. If you wanted to derive it, things to remember are, first of all, we're using the thin lens equation, which means a ray bends here, and then it bends here, and we assume it's instantly from there to there. We don't worry about what happens inside the lens. And then the other thing we do is we only deal with paraxial rays, which means when we use Snell's law, we end up using small angle approximations, where sine of theta is about equal to theta for small angles. All right? So if you wanted to derive it, that's what you think of. But if you don't, then just know this is the equation that we use. If I give you some, lens that has some surfaces, that's very bad drawing. Imagine I give you a lens like this, and I give you the two radii of curvature. This is the equation you would use. But there's one thing you have to worry about. The radius of curvature can be positive or negative. And the convention in your book, you have to remember what it is or whatever. I always forget what the convention is. So I'm going to tell you how to figure out whether R1 or R2 should be negative in this equation. All right? And different books may use different conventions, which means this may be a plus sign, or there might be a minus sign out here, or whatever. Whatever this equation is, however you write it, instead of memorizing conventions, let's think about the physics and what has to happen, and I'll show you how you can figure out what the radius of curvature should be. All right? So our equation was, again, 1 over f is equal to n minus 1, where n is the index of refraction of the lens, the material the lens is made of, and then it was 1 over r1 minus 1 over r2. So to get that right, really doesn't matter, because if I got it wrong, I'm just making up a new convention, and we'll figure out from the physics whether to put plus or minus signs in here. Incidentally, if your lens is submerged in water, when you derive this, it turns out this 1 came from the index of refraction of air. So if you're figuring out the focal length of a lens in water, you'd replace this 1 with the focal length in water. Just a side note. All right. But convention, imagine, if you will, I have a lens that looks like this. All right? The focal length is determined by two things. There's bending here and bending here, right? So these two surfaces I go through. All right? Now, I can tell you what the radius of curvature is, right? I can say that this surface is part of a sphere that's, say, 10 centimeters in diameter, and this one's part of a sphere which is 8 centimeters in diameter, or something like that, right? But I can just, plug my 10 and 8 or whatever in there, but I need to know what sign to use. So here's how I figure out what the sign is. First of all, in my mind, I'm going to cut this lens in half, all right? So I'm going to think of this lens as two pieces. This lens plus this lens right here, and I'm just going to slap them together, all right? So let's just think of this lens right here, all right? Now, if I look at this, what's going to happen? This lens right here, well, if I go to my equation and just try and figure out what happens with my lens if one of the sides is flat, what's the radius of curvature for a flat surface? It's infinity, and 1 over infinity is 0. So that's why I slice my lens in half like this in my mind, because then I only have to worry about one term at a time. So the focal length for this lens right here, it's given by 1 over f is equal to n minus 1 times 1 over r1. And I don't have to worry about r2 because for this lens it's infinity, right? But then I look at this and I say, what's going to happen? All right, here's my normal. Is this going to bend towards or away from the normal? We're going into a medium with a higher index of refraction. We're going to bend towards the normal. So this surface, a convex surface, is going to cause the light to bend inward. Bending inward means, right? Okay, then it bends out again a little bit here, so this other surface will affect it. But the point is, if I have a lens with one convex surface and one flat surface, it ought to be focusing. All right, so my focal length ought to be positive. If I want my focal length to be positive, I look at this and I say, oh, R1 must be positive. So this one right here, this is positive, all right? Then let's look at the other half of the lens, and let's think of it this way. Let's imagine I had just this piece right here. What does this surface do? Imagine I have a ray of light that comes in. Now I'm going to bend, instead of towards the normal, I'm going to bend away from the normal, but again, because we're on the other side, away from the normal actually causes it to focus, all right? The focal length of this lens is determined by this equation, n minus 1. R1 is now infinity for this one, so it doesn't matter whether it's plus or minus because 1 over it is 0, and we're left with just minus R2. Well, this lens, this imaginary lens that I made up in my mind, which is half of the lens I really want to do, it should have a positive focal length. So once again, convex surfaces make the focal length more positive, all right? So I look at this and I say, if I want this to be positive, but I've got this minus sign in here, R2 must be minus. So the convention that this equation uses, in that convention, this lens, this surface, I would call a positive radius of curvature, and this one I would call a negative radius of curvature, right? If I had a lens like this one, right here, I'd look at it and I'd say, well, if I kind of in my mind slice it in half, when the rays come in here, they are going to bend towards the normal, but towards the normal is that way. So this surface should be making the lens more diverging. More diverging means more negative, which means R1 must be negative for this lens. And then I come over here, a ray of light coming out of here, it's going to bend away from the normal, also making it more diverging, all right? So to make my focal length more diverging with this side right here, I need this to be negative, but there's a minus sign in front of there, so R2 should be positive, all right? So convex on the object side is plus, convex on the image side, or on the other side, the observer side, is negative R, and so forth. But you don't have to remember that. Just stop and think of the physics. What is this surface doing? This surface is trying to make the lens more diverging, makes the focal length negative, so R1 had to be negative here so that it would make this, right? If the other side were completely flat, R1 would need to be negative to make it so that we got a negative focal length. All right, so that's how you work with the lens maker's equation. So each piece of your lens is part of a big sphere, and you can just think of your lens as being the intersection of spheres, and they've got a radius of curvature, and then you just need to decide whether they're positive or negative and stick it in here. Now notice, because of the sign conventions, if you take a lens, let's say I had a lens like this, right? All right, if I look at this, this surface is going to try and make the focal length positive. It's convex, so r must be positive here. Here, the surface is trying to make the light diverge. It's a concave surface, right? That's going to try and make f more negative, but I already have a minus sign in front of here, so both of those radii of curvature would be positive for this one right here. But this lens, you can just think, it's just the intersection of this sphere with this sphere. And, you know, this one has a radius of curvature, you know, from here to here, and this one has a radius of curvature from there to there. All right? And then you just remember what the convention is, think about the physics, plug it into the equation, and this equation, also note, this is 1 over the focal length, so when you're done, don't forget to flip it over. And that's how you calculate the focal length of a lens with two spherical surfaces. All right. Now, mirrors versus lenses, once again, the same equations for image position and magnification. 1 over f is equal to 1 over p plus 1 over q, and the lateral magnification is negative q over p. We use those over and over again for mirrors and lenses. Negative n for both mirrors and lenses means an inverted image. Positive q for both mirrors and lenses means that the image is real and it forms on the side that the light actually goes to, or in other words, the side your eye is on when you're looking at it. For a mirror, come back. For a mirror, if I got an object right here, my eye is over here, right? So positive q would be an image on this side. For a lens, I've got my object right here, but you look through a lens, so this is my eye right here. Positive q would be over on this side. So positive q is image forming on the side that your eye is on, the side your eye is on when you look at it. Positive q means a real image. Negative q means a virtual image. So anyway, there you go. Now, how do I do ray tracing? How do I draw lines to figure out where my image forms? Now here, I've got this lens here, and it's shaped like this. It's these two curves, intersecting curves, and I've got glass in here. But I'm going to draw this line right through the middle, right? Because when I do my rays, I'm using the thin lens approximation, and so all of my rays are, they're just going to pretend like the lens is just this line right here. All right? Well, I have some special lines. A line which is parallel to the optical axis will bend and go through the focus, right? This is a converging lens. It comes to a real focus. All right? Light going through the focus on this side. Oh, note, with mirrors, we only had one focus, right? It was on one side or the other depending on whether the focal length was positive or negative. But for a lens, we actually have two focal points, one on either side. One that goes through this focal point right here, right? It's going to come out parallel, and that's where our image forms. We have one more ray we can use, which is the one right through the center, and that verifies that we found the image in the right place. The fourth ray, the one that goes to the center of curvature in mirrors, does not apply to lenses, right? Because it's, you know, in a mirror, something that went through the center of curvature goes right back. For a lens, we have two surfaces, right? So we have two radii of curvature, we have two center of curvatures, and a ray going right through one is not necessarily one that goes right through the other. So we don't have that fourth ray, we just have three for lenses. All right, what about a divergence? Oh, yeah, once again, remember, we draw this line, and we draw all of our rays to this line, even though the lens is really curved. And once again, in my notation, I like to not draw those curves unless I have to, and I'll just kind of draw a line, and I put little arrowheads on the top that kind of say, oh, this arrowheads like that would be a converging lens. A diverging lens I would draw like that. Okay? Now, how do we draw rays for a diverging lens? Once again, I've got two foci, but this time a ray that's going parallel to the optical axis, instead of bending down towards the focus, since the focal length is negative, it bends away as if it were coming from the other focal point. A ray that is going through the center just goes right onto the center, right? Because both surfaces are parallel, or perpendicular to the optical axis at the center. So if we bend on this one, we unbend on that one. And in the thin lens approximation, then nothing happens. It just goes straight on through. Then we have another one, right? So we had a ray that was going parallel. It got bent away. If I have a ray that's going as if it's going to a focus, right? For a converging lens, I'd draw it through the focus, and then it would come out parallel, right? But this is a diverging lens, so instead I'm going to shoot to the focus on the other side, but when I hit the lens, it's going to bend and come out parallel, all right? And so as you can see, these three rays do not intersect, and instead, if I put my eye over here and look at this, it looks like they're all coming from a point over here, and I get a virtual image. Q is negative, right? Negative Q means virtual image. Magnification is negative Q over P, Since P is positive and Q is negative, the magnification is positive, and my image is upright. It is not inverted. Now, when does a converging or diverging lens or mirror make a real or a virtual image? Remember, a virtual image happens when Q is negative. Q is negative. And a real image happens when Q is positive. So if we look at our equation that's good for both mirrors or lenses, 1 over F is equal to 1 over P plus 1 over Q, all right? If F is positive, Q will be positive as long as what? Well, Q, let's just solve this. Q is equal to 1 over F minus 1 over P, all raised to the minus 1. So for Q to be positive, this thing has to be positive, because 1 over something positive is positive, and 1 over something negative is negative, all right? So as long as P is bigger than F, so for F, for a converging lens or mirror where the focal length is positive, then if P is greater than F, we get a real image. Q is positive. But if P is less than F, we get a virtual image. Q is negative, all right? But what if F is negative? If F is negative, the only way we can get something positive is if P is negative. So if P is not negative, if we're considering real objects, then for F less than 0, for a negative focal length, it's always virtual. That's assuming that P is positive, all right? And we talked about in class in a previous video that if you have multiple lenses together, sometimes you can get a virtual object where P is actually negative. But dealing with just a single lens and real objects such that P is positive, for a diverging lens or mirror, you'll always get a virtual image. All right? And there you have it. Have a nice day.